Good morning. We will continue with the lecture on water. Okay, and I last time mentioned to you about some of the very pressing difficulties and the needs which we'll need to look at, and where I think chemical engineers can play a huge role. Coming back to this, I think all of you have heard of carbon footprint. Everybody has heard about carbon footprint?
Yes, sir.
Have all of you heard about water footprint also? Not really. Increasingly, as the shortage of water is being felt, there is a tremendous need to also look at the corresponding water footprint. It's not just about carbon footprint. In future, there could be other footprints as well. So let me just show you how exactly the water footprint is computed based on essentially what is shown over here. Is not very different from this. Any footprint is really all about what is the product that I'm trying to make, and for that, how much water am I consuming? That's the sum and substance. So many cubic meter of water per ton of product. That would be an way to express water footprint. So it's a quantitative information. It's a good thing for all industries to do, and I believe that increasingly industries will be asked to do that, because I think that people are trying to conserve water. So there are really three components to it. One is what is known as the blue water footprint. So that, in essence, is really the stuff that I'm taking in from the municipality or the rivers, lakes, etc. How much am I actually taking? And where it is sometimes being returned, but it is not being returned to the same body. Like, let's say if I use something and I didn't do any harm, and I put it back into my river, that would be fine. Then I can deduct it. But that's all not the case. What you have is you also have this kind of waste waters, etc., which are finally finding their way into some other body, not necessarily into the water body from where you took your fresh water, because this is a clean source of water. So you have the blue water footprint, and it refers to consumption of surface and groundwater, and through what? I mean, either it is partly being evaporated in your processes, or it is getting incorporated into your products, or it is being returned to a different body. That's really what the blue water footprint is. Okay. Then you also have the gray water footprint. Now, what happens is that many times this wastewater which is being produced is it's not something that you can just discharge it into the river or sewer lines and things like that. There may be restrictions on what is the minimum standard of the water that you can discharge. Now, suppose your water is really not complying with that. Of course, if you have an effluent treatment plant which is so good that it complies with everything, then that's fine. But if that's not the case, then in many industries, what they have to do is that they have to again dilute their wastewater with fresh water and make it comply with the discharge norms and then discharge it. Which would mean what? It would mean that again, I am consuming water for the purpose of discharge of the wastewater, not to speak of the fact that some water has obviously not gone in for good use. Otherwise, I could have reduced the requirement of water in the plant. So it says gray water footprint refers to pollution and is defined as the volume of fresh water required to assimilate the load of pollutants to meet local ambient water quality standards. Okay. So that is your grey water footprint. Of course, many of these things finally will depend on whether you are a good citizen or not. If you are trying to stealthily discharge these things into rivers and lakes and sewer lines when nobody is looking, obviously you have not been a good citizen. That's pure and simple. When I say you, means I'm talking about the industry or whoever is in charge of it. They've cheated. I'm telling you what is the actual norms. That's what has happened. There's so much money being poured into cleaning the Ganga. Well, what for? Obviously, there are many people who have just taken it as a dump yard. There was a time when the water discharge into the Ganga was more from these industrial effluents than it was from the fresh water coming from our mountains and then becoming rivers and flowing. That's the situation in many places. So that's the reality that there is this kind of a pollution. But I'm talking about when you are supposed to comply with the norms. The green water footprint is it seems strange. Like say if you've got a factory and obviously you want to beautify your factory and plant a lot of trees and things like that. There's nothing wrong with it. That's a good thing. But what we forget is that all these trees actually evapotranspirate. They lose a lot of water from their leaves, which the water is getting evaporated. And where is that water coming from? It's actually getting drawn from the soil moisture, and the soil in turn has to take the water from the groundwater. Or let's say you are doing gardening and you're putting in a lot of fresh water. You have to account for that water also. So all that refers to the green water footprint, mainly due to the evapotranspiration by plants.
So, by any chance, are there plants for which we could use the wastewater, like to water them?
Yes, yes, very good. In fact, Mr. Casey Shroff, who was in charge of Excel Industries, he would always advocate this, and you talk about using a lot of the wastewater to actually use for this kind of activity that you're talking about. But I remember, I used to have arguments with him. You see, what happens is that's true. In fact, a lot of these things can be grown with the wastewater. You're right. But what we forget is that the soil is not impermeable. So while a fraction of your effluent may be doing a useful job, but there is also quite a bit which can go down into the ground. Unless you have prepared your fields and all to, you have lined it with plastic or with concrete or something, and so that you don't allow any water to seep through. But if it's going to seep through, then it's not a good idea. Is that clear?
Yes, sir.
Yeah, so be very careful. Many times people will tell you about this and it sounds very impressive. They'll also show you figures. Look at how beautiful the tree is, and I used effluent and things like that. And that's because nobody can see what is happening underground. All right. So let us look at now a little more quantitatively the water footprint, and it also will expose you to what is really known as life cycle analysis, where you need to look at things in totality. You cannot just look at one part of an activity and say this is the water footprint, okay? But you have to look at it in totality. Like for example, let's say in your plant, suppose this is the amount of water that I'm actually drawing in from the lakes, rivers, municipality, wherever. This is the amount, and let's say it's called water footprint production. PRO stands for production. And then I could have made it quite simple. I could have figured out what is the amount that is being discarded, and also whether I'm recycling something, and I could have had a simple picture. But the picture is not so simple because uh, let's say what are you're producing something and you also require raw materials. Now, many times what you'll find is that the raw materials that you are using, their production also required water. So there is a footprint to your supply chain, and that is the water footprint of the supply chain, WF sub. And for that, you need to go back and say, let's say, like if you start producing something from using soda ash, and we know that in the production of soda ash, you also have water which is consumed. Then I have to account for that water. How many tons of soda ash did I use to produce that? How much water would have been required? And I have to basically be responsible for that because I am using that soda ash. So that's what is meant by WF sub. Then you have power. You may require power. Most plants require power. The power plants require a lot of water for running the turbines, and there will always be water loss. All of that, whatever we saw cooling tower, it does not give you back the entire amount of water. There will be some loss, maybe to the extent of 5%, 7% loss will be there, of water. So you have to replenish it. So there is a water footprint of that also. So the energy that you required, the water footprint related to that amount of energy, what is it? So you have to put that in. Of course, today a lot of people will tell you that they are recycling water. In fact, there are some companies which are supposed to be ZLD, which means zero liquid discharge. But you go and ask, I mean, are you not consuming any water? They say, no, 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 we need some water. Obviously, there would be evaporation losses, even if it is ZLD, or many times the effluent is actually just going into the air, rather than into some other place. And so there are losses. It's not as if even for a ZLD plant, there is no loss. But I could recycle it. Now, I could recycle it either into my process A to B. Like, for example, a lot of companies have set up reverse osmosis plants, and they recover some of the water. So you can do that. Okay. Or it could also be like you in your factory, you could also be making other products, and you might find that the waste stream is actually quite useful for manufacture of some of your other products. Or if you're in an industry cluster and someone says, hey, this waste, come on, give it to me, this is useful for me. Like, for example, we saw the soda ash distiller waste, all right, how we could use it for producing better quality salt and recovering more gypsum. So somebody might say, please don't throw it away, give it to me. So it could be that you are recycling in other production processes. But whatever it is, I must get some credit for that component which I am recycling, whether in my own process or in somebody else's process or in some other process within my plant. So I get a credit for that. So credit means it will be negative, right, in the equation, and everything else which is requiring water, it will be positive. And then, as we discussed, the gray water footprint, this is the one you will discharge, but only after you are complying with the norms of discharge. So you'll figure that out. Now, the blue water footprint, you can express it as water footprint blue, which is all the water which was consumed in making the raw materials which you are utilizing in your factory. Okay, so WF sub plus WF production, all the water you actually took in as water in your own plant from wherever, plus the water footprint due to the water that went into producing the power that you are consuming in your industry for the process A to B. Okay? All of that together is the blue water footprint. Okay? Minus. Now I will obviously get a credit for the amount that I'm recycling, or which is at least being going in for some good purpose. That obviously would not include things like somebody steals water from the pipeline and uses it for agriculture, and you say this guy is using this water, so give me credit for it. That's not allowed. So this is your blue water footprint. And for gray water footprint, I mean, you can work it out. What are we saying? That first, I have got some pollutant in my water. And even assume that I've done wastewater treatment, etc., and I've reduced the pollution level. It could be the biological oxygen demand or chemical oxygen demand, or these are usually, or the TDS, the total dissolved solids. These are the three, or it could be even heavy metals, which are very harmful. So it could be that, and someone says, wait a minute, your effluent treatment plant cannot take care of BOD, COD. It can take care of BOD, COD, but how are you removing heavy metals, etc.? And then, for discharge, you will have to dilute it with water. So what you'll do is that I now need two things additionally. One is the water which I'm diluting with. That is also not distilled water. That will also have some TDS, impurity, whatever. So I have to take that into account. That is my concentration in my natural water which I am using. And this is the concentration in my effluent. And I also have a discharge norm that I have, it cannot be more than this. Whatever is the critical impurity I have to deal with. So I'll have a C max. That is the maximum concentration which I can have. And obviously, if I've got 10 different constituents which are a problem, then I have to go with whichever one is the highest and dilute accordingly. And then totally how much volume of effluent am I generating per ton of process A to B. So I can set up this equation. You can work it out yourself. Then that is really your gray water footprint. And so really your total water footprint would then be equal to your blue water footprint plus gray water footprint. I'm just simplifying it. There could be other factors, which come in, like the green water footprint. I'm ignoring it for now and just focusing on the blue and the gray water footprint. Is that clear to everyone? Everybody's understood?
Yes.
Okay.
Yes, sir.
Okay. Now, in fact, if you think that what I'm telling you is all hypothetical and not very serious, that's not true. You can see one of our leading companies, Tata Chemicals, they produce a lot of different chemicals, like let's say in Haldia, in Mithapur, in Babrala, in Uttar Pradesh. They produce a huge amount of chemicals. They're one of the leading chemical producers, and they have done actually a water footprint for all their bulk chemicals. So you can see, even for salt, pure salt, 2.27 meter cube per ton, you would have thought you would only require seawater to make pure salt. That's not true. Phosphoric acid, look at it, 23.5 meter cube per ton of phosphoric acid. Diammonium phosphate, one of the biggest fertilizers being consumed. And so all of them, caustic soda, soda ash, all the things that you have learned, bromine, all of them. So what this does is that today, if you are actually, as the people are becoming more environmentally conscious, if you, let's say, want to go somewhere and want to get a loan for a project, they might even ask you that, have you done the carbon and water footprints for your company? Can we have a look at it? And we just want to make sure that we are lending money to a responsible company. So it may have a financial implication. The second is, it could be also something very, very useful for the senior management, because if they want to consciously make some effort to reduce the environmental footprint of their manufacture, they might then say, oh, listen, phosphoric acid 23.5 m³ per ton. I'm not going to produce it anymore. I'll import it. Someone might even take that kind of a decision, and then of course find out what is the cost of importing versus this, or would say, hey, all you guys, you focus on this and try to reduce the water footprint of phosphoric acid manufacture. So that's the kind of insight you can get through this kind of a number. So today, the carbon footprint and the water footprint are both considered very important, and you'll need to look at both. Is this clear? Clear to everyone?
Yes.
Okay. Now let us look at, all right, if you think I'm just scaring you and there is no problem in our country, well, I think all of you know, okay, like for example, you know what a huge tussle is going on between Karnataka and Tamil Nadu for the Kaveri water. You know, there are fights going on among even different states battling over water. The states which have got more water, other states are saying, why don't we connect up the rivers? You know, that way we'll also get your water. But they are saying, hold on, we might be left short of water. So it's a serious issue today, water. And in fact, I mean, the general belief is that it is these kinds of things which will actually lead to wars. Not necessarily that someone is invading your land and things like that. I mean, of course, that can happen. But these kinds of things are desperate situations because lives are at stake and the lives of millions of people. So let's just try to figure out, you know, the total kind of a budget for water in India. Now, this figure is probably about, I think about maybe 7 to 10 years old. Yeah, you can see 2010. You know, so roughly about 10, 11 years old. But I mean, these are not the natural things. Don't really change so drastically from year to year. Although I must say, in the recent years, you are feeling a effect of climate change where bizarre things are happening. You know. So we'll have to see 10 years from now what happens. So this is the total amount of precipitation, you know, which we receive. It could be water, it could be snow. Ultimately, as part of the snow also melts, and that's how our some of our rivers are formed. So you take both, but you don't take into account obviously the water which is falling into the sea as rain, because that's not going to help you. It's only the fresh water which I can have, which you take into account. And if you look at the availability of that, actual availability, it's about 1869 billion cubic meter. That's the unit. So I can also write this in terms of kilometer cube, okay? Because 1,000 meter is equal to 1 kilometer, billion cubic meter is equal to 1 kilometer cube. Okay, so I can write it as that. Now, you see, this figure is not something which has changed radically over the years, because that is part of the natural cycle. What has changed is that population has changed. Population is much higher today than what it was 50 years ago, or even 20 years ago. So obviously, if I start dividing this number by our population, you can see that already if you have got something like 1.4 billion people, okay, today, obviously you can get an idea that you know, this billion will go, and how many cubic meters each one will have. You've got some idea. Out of even this, it is believed that the actual utilizable resources, not everything that is available is not utilizable, is roughly about 1123 billion cubic meter, and that is divided between 690 billion cubic meter of surface water and roughly about 433 billion cubic meter of groundwater. This has been increasingly going up and up. Everybody is putting up a pump and lifting water. Even all the farm, etc. Earlier, you used to use surface water. Today, people are merely using groundwater. So this figure is going to, I think, get inverted, sometime. Except for the fact that if water is not available, you can't draw anymore from the ground. So per capita water availability is bound to reduce as our population becomes higher. Second is that in our country, there's a huge disparity in the water availability from state to state. There are some states which are terribly short of water, like Rajasthan. Rajasthan has a perennial water problem. Today, of course, Tamil Nadu, notwithstanding all the rain that they're receiving now, Tamil Nadu has a very serious water problem. So there are water problems. So it's not enough to just know these average values. You'll also have to see what is the local distribution. And if you're a good planner, you will plan your industries, etc., based on the local distribution of water. The other, of course, is we have a huge divide between urban areas and rural areas. You go to rural areas in so many places, women are traveling 2-3 kilometers to fetch a pot of water, and we are in the urban areas. Just turn on your tap or just press the flush, and 5 to 10 liters of water is just getting drained out, or your washing machine, just turn it on, and we're talking about 100 liters of water being consumed. So huge disparity, okay, between urban and rural areas. And even in the urban areas, between the rich and the poor, there's a massive difference in the water consumption. You go to a 5-star hotel and you stay in their room, the bathroom, water fountain, or the taps, my God, the way the water gushes out at such a pressure, it's such a waste of water. It'll almost prick your skin. Sometimes it's that forceful. Not required. It's completely useless design. That's what is happening in many of these cases. So, I mean, these are all the issues that we need to take into account. Now, let us look at, like, all these ministries and all, they are asked to say, that what is it that they will require. How much water will be required for irrigation, for drinking, industry, for energy. You can see these are the 4 main ones, the biggies. Out of this, irrigation takes up 82%, maybe even higher today, of the total fresh water that is available in our country. 82% goes for irrigation. That's because we have a large agriculture base. You can see, not even 8, I've calculated last 84.6, close to 85. Okay. And drinking water volume, actually as a volume, it is not so high, except that because our water quality has also become bad. So many cases have water, but their water is not drinkable. So that's the issue. All these subcommittees were asked to say what is their projection for this report was prepared in 2010, that by 2025, how much will require by 2050. And you can see everybody has nicely told you that how their requirement is going to go up. 688, 910, 1072, almost following the typical trends, the way we talk about GDP, 8% annual growth. These guys have also done the same thing. And there's another agency which also did an assessment, and they have also indicated that at least these people are a bit smarter and a little more quantitative. They've given estimates of low and high, knowing that there could be error bars. Where is this water going to come from? Water follows the water cycle. It doesn't follow GDP. Because the GDP is increasing, water is not getting more available. That will be dependent on how much sun is falling, how much water is evaporating, how much is condensing. That's it. That's what is determining water availability. That has got nothing to do with what is your desire in terms of GDP or how much crops you want to grow. Okay? So there's going to be an increasing mismatch between what is our requirement and what is going to be available. So there's going to be a huge issue. Obviously, if you're in agriculture and something like 84-85% is for irrigation, you better be worried about things like how to reduce the water requirement in agriculture. I remember a long time ago, maybe about 20 years back, I used to be in a committee which used to be called More Crop Per Drop. Dr. Swaminathan used to head the committee. That's what we were trying to look at. I mean, how do you grow more crops with less water? And likewise, industries, the water requirement may not seem like a lot, but the havoc that they've created in terms of discharging pollutants. And so whatever water was available, even that water is now not available because it has got polluted. So that's what happens. So industries, don't get fooled into all these, small figures. These figures mean nothing. What about all the calamity that has been caused because of pollution? And many of the water sources which were once wonderful sources and which are no longer there, not available. So I think that you need to look at all of this. Now, one thing, Dryden, when he wrote this 1968, even at that time, he was conscious about the fact that in India, maybe at some point desalination will be required. He, of course, then talked about certain places where the water is just not of good quality, which might mean that you require desalination, or if you are along the coast and there is no water at all, then of course you have no choice. You may require desalinated water. There were two things, which at that time made it more like a theoretical thing. Although that's not true. Let me tell you, the institute where I used to be the director, 1962, they started working on desalination. The first plant in our country was put up by them, by the people who were working there. Incredible people. 1962. So even in 62, there was a recognition that there is a serious problem. It's not today's problem. It's been there even at that time when people were working. At some point, we became callous in everything, and we kind of lost our competitive advantage in many of the things. So what happened was that at that time, I'm just showing you the figure around the time that Dryden wrote the book. It typically consumed for desalination something like 15 to 16 kilowatt hour per meter cube of fresh water that you get from seawater. On the other hand, look at the price of water. At that time, what he's talking about. Rupees 10 per 1,000 tons. And large units, large units got a concession. Instead of being penalized, they got concession and they got water for cheaper. Today, that has increased. I mean, even at the time that he's writing, to rupees 300 per 1,000 tons. But today, if you go to Chennai, you ask for a tanker of water. I'm sure even in Maharashtra, many places it will be true. One tanker which provides you 5 m cube of water, 5,000 liters, they comfortably charge you 700, 800 rupees per tanker. That is for 5 m cube, not for 1,000 m cube. So on the one hand, the cost of water has really shot up, as it should be. And this is one of those, like the computer chips, which have become so much cheaper, or solar cell compared to when they were invented. Desalination also, even if I take the 70s figure, it has come down to something like maybe about 3, I'm talking about the best plants. We're not talking about This is not the standard. The standard will be more around maybe 5 to 6 around here, you know. And but whatever it is, you are talking about close to about a factor of 3 to 4 improvement in terms of energy reduction. So there have been massive improvement in this technology. So this has come down, and water today is valued much more. So it makes it more attractive to try and look at desalination today. And also because many of our plants which have been set up along the coast, like if you go to the Gujarat coast, there are so many plants which they don't have any fresh water. There's no fresh water. They were getting some amount of Narmada water, but that's completely insufficient. And so, for them to write this particular scheme, it doesn't mean anything. You might as well cross it out like I've done. And I mean, they'll have no choice but to do seawater desalination. Okay. And in fact, let me tell you that two companies like Madras Refineries and RCF were pioneers in actually recycling wastewater, saline wastewater, and meeting a lot of the water requirement. Madras Refineries was providing 10% of the water requirement for Chennai from recycle of brackish water. It's happening already, and many of these companies have set up their own desalination plants. So you might as well cross this out and make this as your source of water. In India, it makes a lot of sense because we've got such a long coastline. Look at our coastline. And so many companies have been set up along the coast or near the coast. So it's not something that is impossible that you will do seawater desalination and meet your water requirement. It's already happening, and I can tell you it is going to happen more and more. Maybe in 10 to 20 years time, the situation will be even much more severe, and so many states are planning their own seawater desalination plants. If you think that what I'm saying is not true, again take Tata Chemicals. Tata Chemicals Mitapur plant turns to Suez to solve water scarcity issue and maintain production. And they say the Indian government promised a supply of fresh water to run their plant. When the government was unable to provide the fresh water promised, Tata Chemicals faced shutting down production or finding an alternative source of their water needs. And what are they doing? They are doing seawater desalination. Seawater reverse osmosis plants have been set up. Okay? And we are not talking about small plants. These are plants which will be producing what? Yeah, I think there's some figure here. 170 meter cube per hour. Multiply that by 24 because they're operating non-stop. You know how many million liters of water they are producing by desalination. That is the reality. So it is very important that we spend some time in trying to understand desalination, because as we said, there has been a massive reduction in the energy cost for carrying out desalination, but there's nothing to suggest that we have reached the limit. Although we are already at a situation where obviously the low-hanging fruits have been more or less solved, and we've done that, and that's how the power cost has come down by a factor of 3 to 4. Obviously, it will be more diminishing returns, but every percentage improvement is important. So I think that let us try and understand about desalination. Is desalination a spontaneous process or a non-spontaneous process?
So non-spontaneous.
Absolutely. Why are you hesitant? And why is it non-spontaneous?
Sir, we have to supply energy for desalination.
You're saying the same thing. You're right. You're absolutely right. You have to supply. Question is, saying we have to supply energy and saying it is non-spontaneous, they're the same thing, right? I'm asking you why. Why do you have to supply energy?
So we have to force the water through the membranes.
Right. Why do you have, I mean, that's brilliant. Very good. Uh, why membrane? If you look at all the oceans, how are we getting our rain? You know, all that water is evaporating and forming cloud, right? And so I'm not. I mean, nature is doing it for you, but nature is also doing a desalination, right? Right or wrong? I'm asking you thermodynamically. This is the Gibbs free energy of mixing. When I've got a two component system A and B, right, and I'm putting them together, I'm not talking about things which are non-miscible. I'm talking about things which are miscible. When you put them together, so what will happen is that the Gibbs free energy of mixing can be expressed by this equation where x1 and x2 are really the mole fractions of these two constituents. So instead of x2, I can even put 1 minus x1, right? That's what x2 is. What happens is that both these are less than 1, right? Because there'll be fractions when I mix. And so my log term will be negative. Right? So basically what happens is my delta G of mixing becomes a negative number because my log values are negative. So that's the reason why the mixing process is spontaneous because delta G is negative, and the converse process is non-spontaneous. Demixing is unfavorable process, and therefore you require an external energy input to do it. Now, let's also quickly look at it by analogy. I mean, this could have even been a partition of maybe pure water and salty water, or you can take two gases and let's say two gases, blue and red. If I'm mixing, let's say I can look at it as in one case, as if I'm expanding this over here, and the other gas, I'm as if expanding over here. Okay, like if they're pure components, so I've increased their volume by 2, but because I'm also taking blue and red together, what will happen is that the pressure will remain constant. I have not changed the pressure overall, but what did I do? I have actually introduced many more microstates. Whereas over here, I can only write a single microstate for a pure component. But once it is mixed like this, you can see it's almost infinite the number of microstates that I can write. And what does that mean? I have basically increased the entropy of my system. So I've introduced randomness, more disorder into the whole thing. So equivalently, I can actually write it as delta S mixing will be equal to NR x1 ln x1 plus x2 ln x2 if my delta H, suppose there is no enthalpy change. It's all about an entropy change. Then basically this delta G term is really my T delta S term. So if I differentiate that, I'll get my delta S. So that's how I get my NR x1 ln x1 plus x2 ln x2. But let me also tell you that this has been used increasingly to define the energetics of desalination, and people are working on trying to refine these models. Why? Because one reason is the assumption that delta H does not change is not true. There is a change in delta H also. Like, let me show you an actual factual data here. 25 degrees centigrade seawater having 31,000 milligram per liter total dissolved solids has specific enthalpy of 100.362 kilojoule per kg and entropy, specific entropy of 0.353, whereas at 46,000 milligram per liter TDS, the entropy value is less. So obviously it would be unfavorable to go from 31,000 to 46,000 from an entropy consideration. But if you look at the enthalpy is also going down. So this actually is favorable, at least the enthalpy component. And in fact, there is very detailed values which have been generated as a function of temperature and salinity. So let's say specific enthalpy and temperature. And this one is pure water, no salt. And as you are increasing the amount of salt to 120 gram per kg, this is you're going to this bottom figure. So there are two things, and obviously this is important both from the T delta S term as well as from the enthalpy term, that we understand what might be an optimum temperature for doing desalination. We will continue next Monday from here.
Yes, sir.
Okay, then see you next Monday.